Hello guys, today we are going to continue our chapter properties of the fluid. In the first part we have discussed about the shear stresses in the fluid and related the shear strains produced due to the shear stresses generated within the layers of the fluids flowing in some direction under the action of the applied forces or the gravitational forces. And due to these shear stresses, we have also derived and concluded the two basic differences between the solid and the fluids. And depending upon those, we are going to be relate our shear stresses property with the physical directly with the physical properties of the fluid, that is called as viscosity. In the next slide, we are going to discuss about the very important and the basic property of the fluid, that is called viscosity. Viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of the fluid over another adjacent layer of the fluid. So this definition is very basic, and if you have an understanding of the first part of this chapter, then you will understand very well about this definition of the viscosity. We have studied that how the shear strain is going to be produced, or the shear stresses are going to be produced. Mainly the shear stresses within the fluid are going to be produced due to the resistance of the layer of the fluids those are going to be flowing within the within the boundary or within the periphery of the fluid object in which the fluid is flowing. So the viscosity is also going to be give you an quantitative parameter of these shear stresses. Those are going to be offer the resistance of the movement of one layer of the fluid over another adjacent layer. If one layer is going to be flowing, so within the layers, if the resistance is not going to be produced, then the shear resistance is not going to be produced. And if the shear resistance is not going to be produced, then obviously there will be no flow. You can say your body is at rest. So for the flowing bodies, fluid bodies, you must have a ratio, or you must have the resistance within the fluid object within the layers individually. So if one layer is going to be flow over the another layer and it shows some resistance against each other at the surface of the layer, each layer, then we are going to be say that this definition or this property of the fluid is going to be called as viscosity. So if the more resistance is going to be offered within the layers, then we say the viscosity is more for that particular liquid. If these shear resistance is lesser, then we can say this viscosity is lesser for this particular fluid. So this viscosity is, you can say, a direct indicative parameter to show the shear resistance produced or offered by the fluid object within the layers in which it is flowing. When two layers of a fluid a distance dy apart move one over the other at different velocities, say u and u plus tu as shown in the figure, then what happens? The viscosity together with the relative velocity causes a shear stress acting between the fluid layer. So we can see this figure on the right hand side of this slide. Here you can see that what this figure is showing, the velocity variation near a solid boundary. The same concept, or the same is example you need to be memorize in the first part of this chapter, in which we have also considered the solid boundary. Okay, so fluid is flowing in a solid boundary and the upper part is free surface. At the top of the fluid it is a free surface, but at the bottom of the fluid it is have a contact with the solid boundary. So if this is the thing, this is the you can say the y distance. If you are going on a vertical axis, that this y is going to show you, this arrow is going to show you a y. So this distance, you can say this is a total distance from the bottom of the fluid that have a contact with the solid boundary till the free surface. So if this total distance is y, then you can select, or we can select, or suppose any two layers from within this fluid. One is with the velocity u, and the other layer that is at top of this last layer, that is going to show you a change in velocity, a certain change in velocity with a du, additional velocity du. u is the velocity, that may be the same as of the previous one layer, adjacent layer, but this du will be the additional velocity. So you can say a differential velocity element to the parameter you are going to be add within the velocity of the adjacent layer of it. So these two layers, adjacent layers, will give you the velocities u, and the above that layer will show you with the differential additional velocity u plus du, and finally you are getting u for one layer and u plus du for the other layer. And the difference between these two layers, the vertical difference between these two layers, this may be dy. So you can say these two layers are at a differential distance dy apart, with a difference of the differential velocity du. So coming to again our statement, so if this is the case, then the viscosity together with the relative velocity causes a shear stress acting between the fluid layers. So what does it mean? That your velocity between the two layers will cause a shear stress between the layers, and finally these are going to give you the viscosity parameter. So your top layer causes a shear stress on the adjacent layer, while the lower layer causes a shear stress on the adjacent top layer. Okay, so these both of the layers are going to be cause the shear stresses against each other. This shear stress proportional to the rate of change of velocity with respect to y. It is denoted by a symbol tau, and it is called as tau, T-A-U, and you are familiar with this symbol. This shear stress is proportional to the rate of change of velocity. This statement is need to understand. Okay, so whatever the shear stress is going to be produced within the two layers, two adjacent layers, this is proportional to the rate of change of velocity. And what is the dependent factor? That is the y distance. If this dy is more, then you can say this velocity or this shear stress is going to be produced, maybe give you a more value. If it is lesser, then it will be lesser. So you can say that your tau will be proportional to the rate of change of velocity, but with a function or with the dependent parameter, that is y. This vertical distance is also important, as well as this velocity, change of velocity, is also very important. Okay, so this change of velocity between the two layers going to cause shear stress at the contact surface of both of these two adjacent layers, and also the difference between the distance between these two layers is going to be dependent on this velocity, and further this change in velocity with respect to the distance between these two adjacent layers is going to give you a value that is equal to shear stress. Okay, so all of these dependent parameter you need to be gathered upon, and in analytical point of view, you need to just write, okay, or mathematically you need to just write all these parameters so that you can get a final derivation. Now whatever we have discussed logically and also previously in a statement, we can mathematically write as your shear stress tau is directly proportional to du over dy. So what is this du? It is the change of velocity between two adjacent layers of the fluid flowing. And what is dy? Dy is the distance between the two adjacent layers. Okay, so if you are going to be remove this proportionality, you need to introduce a constant for that. So tau is equal to proportionality constant du over dy will remain same parameters. So what is this mu, constant of proportionality? Other two parameters we have discussed earlier. Now in this slide we will discuss in detail what mu is. This mu is actually the constant of proportionality, and it is known as the coefficient of dynamic viscosity or only viscosity. Sometimes this mu is going to be called as viscosity, okay, and sometimes coefficient of viscosity, and sometimes we are going to say it is dynamic viscosity. Okay, and generally in literature and later on when we go on with this chapter, we will discuss this mu as a dynamic viscosity. If we are going to compare it with the kinematic viscosity, another physical property of the fluid we will discuss, that will be the kinematic viscosity. So here this mu is going to be called as dynamic viscosity. du over dy, it represents the rate of shear strain or the rate of shear deformation or the velocity gradient. You need to remember these three terms. These are alternatively going to be used for the representation of this du over dy. Okay, that is going to represent the tau, means shear stress. So in which parameter, on which parameter your tau, the shear stress is going to be dependent. This is du over dy. So in one terms or in one way you can say this is rate of shear strain. In other terms you can say rate of the shear deformation. Or the third way is to represent it is the velocity gradient. Okay, so in some literature if you will find it as a velocity gradient, you must know what velocity gradient is. It is du over dy. Okay, so what is the rate of shear strain? It is again du over dy. What is rate of shear deformation? It is again du over dy, on which your tau or the shear stress is dependent. So from the above equation we have mu. We are here not interested in the shear stress and the distance between the layers. These may be the input data for us. We are interested in determination of this proportionality constant that is called as dynamic viscosity or the viscosity of the fluid. So if this is needed to be determined, so we have the mu is equal to tau over du over dy. This viscosity is also defined as the shear stress required to produce the unit rate of strain. Okay, so whatever the shear stress is there, this is du over dy, it is the rate of the shear strain actually. So rate of the shear strain, if it is needed to be produced, then how much shear stress you are going to be apply to produce the unit rate of the strain, unit deformation. And this deformation is going to give you a representation of the internal resistance of the layers flowing within the fluid, and finally this internal resistance at a global level. This is a local level you are going to be considering this value du over dy. If you are going to be integrated for whole of the fluid starting from the bottom till the top, then you are going to be get your value of the shear strain or the deformation of this fluid object at a global level. You must understand that. Once you will study the mechanics of solid also, and in the structure, and slowly you will study about that, and you will also learn this important factor, that what is the local level and what is the global level for to determine any parameter, any quantity, any property of fluid or the solid. So for that, the first derivation that always you will do, or the derivation of the formula or anything, the first derivation also always going to be involve all of the parameters at local level. Mean out of all of these finite layers, number of the layers, we are taking out, or we are considering only 2 layers at a local level. Any level we are going to be considering within the fluid and this whole object, and we are going to be consider it as a local level. So this differential change we are going to be considering. But what is the total change of the velocity starting from 0 till top, complete y? Okay, that is going to give you the final resistance at the global level for this object or this fluid. Okay, so what you can say, your mu or the viscosity is going to give you the shear stress produced within the body, that is going to be required to produce within the body to produce the unit rate of strain. So if this is going to give you for the unit value, then if the total stress or the total object will be with you, you can get the value of the viscosity at the global level. Okay, so this is very important. So your viscosity finally going to give you the global value level value, mean the final resistance of this, the total resistance of this object for all of the layers flowing within the object. Now we will discuss about the units of viscosity. These are very important, because once you have the viscosity, so we have MKS system, we have CGS system, we have SI units of viscosity. So in the very first slide introductory lecture, we have discussed about these unit systems. So now this conversion of the unit system is very important, because sometimes it is asked to you, or you will be given with the data in one unit system, and it is required to give you the answer in another unit system. So you must be familiar with this, the interconversion. So if we are going to start with the viscosity formula, that is shear stress over velocity gradient. So force over area. So what is our velocity? That is length over time. And what is gradient? That it is dependent on the length of the body, or between the layers. So length of the time is going to be have again divided with the length, it is going to give you the velocity gradient. So force over area, in numerator shear stress is going to be represented with force over per unit area, and your velocity gradient is velocity and then gradient. So velocity is length over time, okay, dependent on time, so change in length with respect to time, and gradient is per unit length, how much you can say the change is going to be happened. So it is 1 over length. So finally you are getting force into time divided by length square. Okay, so in this way you are having your formula finally for the dimension point of view, or to get the final unit of the viscosity, force into time divided by length square. So if we will talk about the MKS units of viscosity, so it will be kgf second over meter square. Okay, so force is going to be represented by kgf in MKS system. If we talk about CGS units of viscosity, then your force is going to be represented, or this unit of the force is dyne. If we talk about the SI units of viscosity, then it will be Newton. The force is going to be, the unit of the force is Newton. So Newton second per meter square. And for the CGS system, it will be centimeter square in denominator. And this dyne second per centimeter square collectively is going to be called as poise in CGS system. And for SI system, this unit collectively is going to be represented by Pascal second. Okay, so this you need to remember. Pascal is Newton per meter square. You are well familiar with that. And second is an additional part. So Pascal second. And this whole term in CGS system, dyne second per centimeter square, is going to be called as poise. This you need to be remember all the time. Okay, so we will do the numerical problems. There we are going to be deal with this conversion. Okay, and we will do the practice for that. So you need to be remember also these things. In MKS system, force is represented by kgf and length is by meter. And in CGS system, force is represented by dyne and length is by centimeters. In SI system, force is represented by n and length is by m, meters. Now this slide is very important. We have talked about this thing that your 1 kgf second per meter square in MKS unit system is equal to poise, mean 1 poise. How it going to be happened? आप किस तरह से how you are going to do the interconversion? Okay, that is very important, and we will do over here. That you need to remember all the time. Okay, so wherever it is required, that how much of your 1 kg second per meter square is equal to how much poise and how much in intermediate SI unit system. Okay, that you must know. If we start from the 1 kgf second per meter square, that is the unit of mu viscosity in MKS unit system. It will be equal to 9.81 newtons second per meter square. In the numerator, this 9.81 is, you are going to be actually what is this? You are converting 1 kgf into newton SI system. Okay, so you are converting your MKS system first in SI system. So representing your kgf with 9.81 newtons, you are multiplying it with simple 9.81, so your force is going to be converted into newtons. In mass you are converting into newtons. Now your 1 newton is equal to, you are familiar with that, mg square. Okay, 1 newton, what newton is? Newton is equal to mg square. Okay, so 1 kg in mass and into 1 m over s square mean acceleration. So if you are going to be replace, mean you are going to be input this value, so in kg, your kg in grams in CGS system, you are not considering kg, you are considering it grams. So if you have 1 kg, you are converting into grams, it will be 1000 grams. And if your meter per second square for acceleration part, this meter if you are converting in a centimeter, it will be 100 centimeter, and second square will remain the same. So you are getting 1000 into 100 grams centimeter over second square. Okay, or what you can say, what is this gram centimeter per second square? This is actually going to represent your dyne. For that you can again take a reference from the previous slide. Okay, in the last slide we have discussed about the dyne. So what dyne is a unit of the mu viscosity in CGS system. So that is gram centimeter per second square. So this is another factor that we are adding over here by converting from the SI system to CGS system. Okay, so this 1000 into 1000 dyne you are getting over here. So what dyne is, it is gram per centimeter over second square. I have told you, okay, this parameter is equal to 1 dyne. Now again coming to the very first, okay, where we have started. 1 kg F into second over meter square, it was equal to 9.81. That factor will remain same, okay, 9.81. Now what is an additional part over here? Newton. The Newton is going to be converted right now into 100 into 1000 dyne second per meter square. So what dyne is? Dyne, this part, okay, this one. And what is second per meter square? The second per meter square is from here, okay. This Newton is actually 9.81 will remain same. Second over meter square will remain same. Only the Newton is going to be replaced by 1000 into 100 dyne. Now what is going to be happened next is you have all these parameters now with you, okay. So what I have told you, this and this dynes, these two parameters are only going to be replaced. The Newton is going to be replaced by 100 into 1000 into dyne, okay. So rest will remain the same. So now you are getting simplifying it, okay. The meter square is again you need to be converted to centimeter square, so it will be 100 into 100. So if this is the case, you need to simplify all these numeric values, and finally you are getting 98.1 dyne second per centimeter square. So this dyne second per centimeter square is equal to poise, okay. This again we have discussed in the last slide, that what poise is the unit of viscosity, that is dyne second per centimeter square. So you are getting 98.1 poise. So 1 kg F over meter square finally is equal to 99.81 Newton second per meter square, or equal to 98.1 poise, okay. So in this way you need to be keep this 98.1 poise with you, okay, and this Newton second per meter square. So if you want to get 1 Newton second per meter square, this 9.81 will go on the other side in the denominator, and it is going to give you the 10 poise value. And if you want to get the value of 1 poise, then again you need to take this 10 on the other side of the equation, and it will be 0.1 Newton second per meter square. So finally you are getting the value of 1 poise, that is equal to 0.1 Newton second per meter square. Now once the concept of the viscosity will be clear to you, then we can very easily discuss about the two type or two classes of the fluids. Those may be Newtonian and the non-Newtonian fluids. This is where these are very important. So we were talking about the Newtonian and the non-Newtonian fluids. So even among the substances commonly accepted as the fluids, there is a wide variation in behavior under stress. Fluids obeying the Newton's law of viscosity and for which mu has a constant value are known as Newtonian fluids. Most common fluids fall into this category, for which the shear stress is linearly related to the velocity gradient. That particular type of the fluids we have discussed in the last slide, in which we have derived the equation for the viscosity by considering that type of the fluid in which your rate of change, mean the relationship between the shear stress and the velocity gradient, will remain linear. Okay, it is not going to be changed. It is not going to be dependent on any other further factor. Okay, so if this relationship between the shear stress and the velocity gradient will become linear, okay, and the value will become constant throughout the application of the flow criteria, or mean to say the flowability throughout of the fluid, then we can say that the shear stress or your fluid is going, these type of the fluids are going to be called as Newtonian fluids. Now we will talk about the other type of the fluids, non-Newtonian fluids. Just later on, or you can say that after these slides, we will going to be focused on non-Newtonian fluids now. Newtonian fluids are understandable, and also we will discuss in whole of our fluid mechanics 1 subject. We will discuss only the Newtonian fluids, in which the relationship between the shear stresses and the velocity gradient will remain linear, and only one constant viscosity value we will get for that particular fluid. Okay, any stress condition under any temperature, under any other type of the changes. So if the stress is not going to be changed or going to be changed, the viscosity value will remain same. Your fluid will always be a fluid. But for the non-Newtonian fluids, the conditions are going to be changed. Somehow your viscosity will no more give you a linear relationship with the velocity gradient. Your shear stresses are not going to give you a linear relationship with the velocity gradient. Okay, so in that particular case we need to discuss about the non-Newtonian fluids. Those are not going to be fall in the category that we have discussed earlier. Okay, so here you can see the shape of the curves. For the dilatant, the shape of the curve or the exponential curve is like this. Okay, it is in increasing manner. And what about the pseudoelastic? It is in decreasing manner. The slope of the curve is decreasing, but here the slope of the curve is increasing. Okay, so in this way, if you are going to draw a tangent, then that's the slope of the tangent will be decreasing. If you go on move on in the more other side, you are expanding the curve. And on the other side, for the dilatant type of the fluids, this if you are going to draw the tangent, then the slope of the tangent is going to be decreased. So in this way, increase, sorry. So in this way, you can have a clear differentiation between the pseudoelastic and dilatant substances. Now, how you can give an example? For the pseudoplastic, the examples may be the clay, milk, cement, and quicksand. And for the dilatant substances, it will be oobleck, wet sand, and body armor. What is oobleck? Oobleck is the mixture of the cornstarch and water. Okay, so simple cornstarch you are getting. You are well familiar with this type of the cornstarch. Corn flour we can say we are only going to be use it in cooking purpose. And this cornstarch, if you are going to be mixed with water, then this type of the you can say fluid is going to be called as dilatant. Then wet sand and the body armor. Body armors are going to be used by the military and the armed forces for their safety purpose. This is a kind of a suiting, or you can say a protective or defensive kind of suits that those are going to be wear over their bodies. Next one is thixotropic substances. Those are not in the graph, but those are going to give you another category of the non-Newtonian fluids. These are the fluids for which the dynamic viscosity decreases with the time for which shearing forces are applied. Thixotropic jelly paints or the printer inks. Those are not related to our concern as in civil engineer, but still those are important. Rheopactic materials. Those the materials for which or the fluids for which the dynamic viscosity increases with the time for which the shearing forces are applied, like creams. Viscoelastic materials, which behave in a manner similar to the Newtonian fluids under the time invariant conditions, but with one difference: if the shear stress changes suddenly, it behaves like a plastic. Okay, so these kind of the fluids with the certain examples are given. Okay, so here in the next slide you can see a brief summary of all those discussions we have done in the previous slide, like type of the behavior, then description about that, how viscosity decreases with the shears, with the stresses over the time or not. Then examples are also given over here and listed over here. So what is the leak effect, what is the importance or implications for those kind of fluids, if you are going to be counter apart those fluids within the construction and civil engineering. The behavior of the non-Newtonian fluids has important implications. If let's suppose if a house is built on a certain type of the clays and an earthquake puts stresses on this material through the sudden movement, the apparently solid clay can turn into a running liquid. This is called liquefaction. So your body armor that behaves like a liquid so that you can move easily but turns into a solid on impact from the stresses could be useful for the police or the military. So this is a solid but fluid kind of a material, body armor. But if the impact force is going to be applied, then with a very short duration of the time, the forces are going to be applied on these type of the suiting, okay, or these kind of the material. It becomes very hard. Okay, so that's why it is going to give safety to the police or the armors. So, but what about the first application? This is very important. Field application. In the field, if once the construction is going to be done on any type of the soil that is a clay type of the material, okay, then what is going to be happen under the stresses? if the earthquake stresses be there, or itself the body or the structure load be there, okay, sudden change in the due to wind loading, or due to the, you can say, the partial settlement is another phenomena in which the suddenly the structure can apply the load on the clay or the soil, foundation soil. So in that particular circumstances, the soil, the solid clay, that mean to say that is going to give you a behavior of a solid, those are acting like a solid, can turn into a running liquid. This is called liquefaction, mean those can give you a flowing conditions. So this is an example of the non-Newtonian fluids, that under stresses those are going to be change their behavior. So if this kind of the fluids be there, then we have to be very careful. If those are going to be in a field application, you are going to counterpart those type of the fluids, then you have to be very careful. If Newtonian fluids be there, then there will be no difficulty. You have already equations derived with you, you have already formula with you, you can go with other physical properties very easily. But if the non-Newtonian fluids are there in the field, so you must be very careful about the analysis and about the design of these kind of structures. Now we will talk about the mass density, the next physical property. Mass density rho, you are already familiar with this definition, is defined as the mass of the substance per unit volume. So m over v, its units are kilogram per cubic meter, dimensions are m, l minus 3, typical values at pressure 1.013 into 10 raised to power 5 Newton meter square, and temperature 288.15 Kelvin. The water density is 1000 kg per meter cube, and air density is 1.23 kg per meter cube. Then we have another physical property, next one, that is kinematic viscosity. Again, very important. Okay, if you have a dynamic viscosity with you, then to determine the kinematic viscosity will not be a harder or difficult task. Okay, why? Because kinematic viscosity mu is defined as the ratio of dynamic viscosity to mass density. Whatever the mass is going to be, overall the mass of the fluid is under observation, for which you are calculating, or you have already your dynamic viscosity. So what you need to do, you need to just take the ratio, you need to divide the mass density with the dynamic viscosity you already have. So nu will be equal to mu over rho. Those are going to give you the unit square meters per second. Your kinematic viscosity is often measured in Stokes. This square meters per second, this unit meter square per second, is going to be called as Stoke. You need to be remembered, like Poise. Okay, for the dynamics viscosity, I have told you that this Poise unit you need to be keep in your mind. So similarly, for the kinematic viscosity, whatever the unit you are getting, this is generally or collectively is going to be called as Stoke. So 1 Stoke is equal to centimeter square per second. Okay, why centimeter? Because the Stoke again a unit in CGS system, like Poise is a unit in CGS system. Stoke is also a CGS system unit. So 1 Stoke is equal to centimeter square per second. So if you are going to converting in SI system, it will be 10 raised to power minus 4 meter square per second. So if it is need a conversion from Stoke, so you must be clear wherever the given data of the for the kinematic viscosity is in Stoke, you must be clear in your mind that it is in CGS system. First of all, you need to convert. Okay, you need to do the conversion for the units, and then you need to go on to use this value of the kinematic viscosity in your calculations. You must be very careful. Similarly, for the dynamic viscosity, if the Poise be there, the value of the dynamic viscosity in Poise is given to you as the given data. So during the calculation, you must be very clear in your minds that this dynamic viscosity Poise is in CGS system. So first you need to do the conversion, and then you need to go on. So dimensions are L square per time, of course, so T minus 1. So typical values, water 1.14 into 10 raised to power minus 6 meter square per second, and for air it is 1.46 into 10 raised to power minus 5 meter square per second. Then comes specific weight. Specific weight W is defined as the weight per unit volume. So again, maybe you are familiar with that. I mean, you have studied this physical property of the fluid earlier, but again we have a revision for that. Since weight is dependent on the gravitational attraction, the specific weight will vary from point to point according to the local value of gravitational acceleration g. So the relationship between W, specific weight, and rho, mass density, can be deduced from the Newton's second law, since weight per unit volume is equal to mass per unit volume multiplied by g. So once the specific weight is mean mass density is with you, mass per unit volume, so this mass per unit volume you can multiply with the g and you can get the specific weight. Okay, so weight per unit volume. These units will be newtons per cubic meter and dimensions will be ml minus 2t minus 2, and typical values for the water and for the air are given over here. Next is specific gravity. Now specific gravity is defined as the ratio of mass density of a substance to some standard mass density. For solid and liquids, the standard mass density chosen is the maximum density of the water, which occurs at 4 degrees centigrade at atmospheric pressure. So you can say your S, specific gravity, capital S, is equal to rho of the substance that is under observation divided by the rho, mass density of the water at 4 degrees centigrade. For the gases, the standard density may be that of the air of the hydrogen at a specified temperature and pressure, but the term is not used frequently. Okay, so units, since relative density is the ratio of the two quantities, so there will be no units. Dimensions again only one. Okay, m0, l0 and t0. So typical values for the water, oil and mercury are given over here. So sometimes you need to be remember these values, but once you do practice with the numerical problems again and again, and maybe initially at the beginner level you will be given with these standard values, but later on when you will be have a good practice on doing or calculating these numerical problems or these kind of the you can say issues or like this, so you can you will be able to solve or just to memorize these kind of the standard values for the water and the standard type of the liquids or the fluids. Specific gravity, continuing slide. S for liquids and S for gases. I have told you weight density of the liquid divided by weight density of the water. Okay, so sometimes it will be mass density and sometimes it will be weight density. Both you can use alternatively. So what you need to do for the weight density, just you need to multiply it with the g. Okay, so in the denominator and in the numerator the g will be the same, so it is going to be cancelled out. So finally you are again having the mass density, but you can write also in terms of the weight density. If the values are given in terms of weight density for for one type of the fluids, so what you can do, you can also calculate your specific gravity. It is, you must remember, do not stick only with the mass density. Your specific gravity can be calculated by the weight density also. Next is specific volume. In addition to these measure of the density, the quantity specific volume is sometimes used, being defined as the reciprocal of the mass density. So it is not, you can say, a new term, just whatever we have calculated earlier like a mass density, you are taking a reciprocal of that. So mass per unit volume, other than that volume per unit mass. Okay, so this is going to give you the specific volume. So specific volume of the fluid is defined as the volume of fluid occupied by a unit mass. So sometimes for certain you can say conditions we need to determine the specific volume also. So do not be confused with that what specific volume is. Specific volume is V over M that volume of a fluid occupied